right. Well, hello and welcome everyone to another edition of the Operate First Data Science Community Meetup. Today we have, I think, a cool presentation with a big cast of speakers. Many of the data scientists from the originally the AICOE, now members of the Open Services Group within Emerging Technology, are going to talk about a project that we have been working on for a little while called AI4CI. I won't go into too much detail because I'll let them do that. But before we jump in, does anybody have any questions about the meetup or why we hold these meetings or any topics that they want to bring up? All right, cool. And as I said, these meetings are recorded. They will be posted to YouTube within a day or so. And if you go to, the Operate First link I've posted here, you can find more info about this session and previous meetups. And with that, I'll hand it over to the team to talk about AI4CI.
Thank you, Michael. Can everybody see my screen, hear me fine?
Yes.
Yep.
Awesome. So hello, everyone, and welcome to another Operate First Data Science Community Meetup. I'm Aakanksha, Duggal, and along with my colleagues and fellow data scientists from the Open Services Group in the Emerging Technologies Group at Red Hat, we have Hema, Veeradhi, Karan, Chauhan, Oindrilla, Chatterjee, and Shrey, Anand. And we are all going to introduce AI4CI, which is Artificial Intelligence for Continuous Integration. It is a collection of open source AIOps tools involving open operations data made available by Kubernetes testing and visualizing with platforms. So in this session, we'll go over what is AI4CI and what are the various data sources involved in creating various tools and services that are a part of this initiative. We will also go over various machine learning models that have been deployed as services on the Operate First cloud. And lastly, how you can engage and participate in this AIOps project. So let's get started with what is AI4CI. And before we introduce the project AI4CI, let's introduce AIOps and what it stands for. So AIOps stands for Artificial Intelligence for IT Operations. It is a critical component for supporting any open hybrid cloud infrastructure. In our opinion, it's mostly a cultural change, very much as we saw in the DevOps movement. Here, we combine the two cultural mentalities from dev and ops to create a new culture, the DevOps culture. And the same cultural change is going to happen with AIOps. The DevOps culture and the data science culture are using different tools and have some different mindsets. Our aim with AI4CI is to bring these two cultures together and learn from each other. We aim to embrace the intelligent tooling that we have in the AI world and apply it to the operational domain. So what is CI? Continuous integration is the practice of automating the integration of code changes from multiple contributors into a single software project. CI/CD is a solution to the problems that integrating new code can cause for development and operations teams, also known as the integration hell. So what's AI4CI all about? Simply put, it's AI applied to CI/CD data. It's an intelligent open source AIOps toolkit which can be used to better monitor builds in order to help the development lifecycle. The goal of this project is to build AI tools for developers by leveraging the open data made available by OpenShift and Kubernetes CI platforms. As a part of AI4CI, we've built a collection of open source AIOps tools which can help support a CI/CD process. Such open source operations or CI/CD data coming from real-world production systems is a rarity for public data sets today. Thus, this presents a great starting point and first initial area of investigation for the AIOps community to tackle. We are focused on cultivating an open source community that uses open infrastructure for data scientists and DevOps engineers to collaborate. So to talk more about the tools and services, I'll have Oindrilla Chatterjee.
Hey everyone, thanks for the introduction, Aakanksha. So as we discussed earlier, one of the goals of this project is to build an open AI ops community, which involves open data sources, which originate from various different segments of the CI process. So with that goal in mind, we collect data from various CI/CD data sources such as GitHub for code changes, Prow for build logs, TestGrid for test results, Bugzilla for the filed bugs, and the telemetry data for cluster logs. And we then analyze the data originating from these various open data sources and gather metrics from them, as well as create some models and services which can address certain problems or within the CI/CD process and ultimately help the development lifecycle and the whole CI/CD process as a whole. So we start to build all of these AI ops community and we develop the necessary tools, starting with the AI ops cloud, operate first cloud. So for those who are not familiar with the operate first cloud, it basically provides an open source platform with instances of cloud services and applications that can support your data science work streams, such as Jupyter Lab, S3 storage, database engine Trino, visualization tools like Superset, the Selden operator for deploying models, and an OpenShift namespace to train models, and so on. So we built these set of AI ops tools, and by using the applications deployed on the Operate First cloud, and we have also deployed the AI ops services on Operate First, so they are accessible to anybody who wants to try them out. So the various AI services that we have deployed on the Operate First cloud that we'll also be giving an introduction to shortly are the GitHub time to merge prediction service, the optimal stopping point prediction service, and the build log clustering service. And with that, I will hand it over to Karan, who will go over the GitHub time to merge service.
Awesome. Thanks, Oindrilla. Let me just take over the screen share. Yeah, so let me know if stop me at any point if you can't see my screen or if you can't hear me. But yeah, so in the next couple of minutes, I want to talk about the GitHub pull request time to merge prediction service. And in this sub-project, the wider goals that we're trying to go after were, so how do you actually measure and how do you track and forecast project development KPIs? So things like velocity, blockers, idea to production time, and so on. And then this naturally leads to the question, how do you even collect the data from your GitHub repositories that lets you do this kind of analysis? And then once you have this kind of data, can you actually augment the DevOps process with AI/ML services? For example, building a time to merge prediction service so that you can triage your pull requests or get a better idea of the estimated effort for each sprint, and so on and so forth. So these were the broad challenges that we are trying to tackle in this sub-project. And then the approach for this we took was, so first of all, for the data collection, we use this Python library called the MI library, which is also developed by the Thoth team. And it's basically as simple as running this one line of Python code. And then the output of that is that you get a whole kitchen sink of data about your entire GitHub repository or PRs. So for example, the types of files change in each PR, the number of lines, number of commits, the author, and all of that good stuff. So yeah, once we have this basic data, what we do is apply some transformations to this so that it's suitable for use in a machine learning model. So this means things like converting the small, medium, large PR labels to numeric values, or maybe extracting some keywords from PR descriptions and titles and so on. In addition to that, we also try to apply some feature selection so that instead of working with this whole wide set of features, you're only working with a small and relevant set of features for your model. And then at this point, once you have the clean data, you can actually go ahead and start building a dashboard to visualize the project KPIs that we wanted to measure in the beginning. So we created the superset dashboard, which I won't dive into for this presentation, but it's there for you to check it out if you want. So it basically tells you things like the number of commits over time, who have been contributing to your GitHub repository, and what kind of PRs are you getting, and so on. Okay, so that's one stream. And then the other stream that you can work on once you have clean data is the actual model building process. So for this, we basically explore two main setups for this problem. One is a classification setup, and one is a regression setup. So in classification, we basically want to predict that, hey, is this PR going to be merged within 0 to 3 hours, or 3 to 6 hours, or 1 to 3 days, and so on and so forth. So that's the approach we went with as a starting point. And then we explored a bunch of different machine learning models to classify the PRs. For example, the SVM, random forests, and gradient boosted trees. And then we took the best model of these and then packaged it into a Selden server, and then deployed it as a service so that you have an endpoint that you can interact with. So I guess that's a broad, high-level overview of the project. And then the only part that I think we're going to focus on for today's presentation is going to be the endpoint itself, because that's the thing that is available to you, the open source data scientist or the open source software engineer, to play around with, to explore, and maybe even use in your own projects. So yeah, let me talk a little bit more about the endpoint itself. So yeah, this is the endpoint at which we have deployed our model. And what that means is you can basically take a JSON with your PR data and send it to this endpoint. And in return, you'll get a bunch of predictions for when we estimate that PR to be merged. So I guess to walk through this, it's better if I just walk through a demo notebook. So yeah, so this is the notebook we've created to show how you can use this service. And basically, the first thing you would have to do is get the data from your PR. And again, to do that, it's a matter of just calling that one line of Python code that I showed in the beginning using the mi tool. Yeah, so we've already done that. So I'm just loading the result JSON that we have saved in our storage. And then once you have this data, you can look at what this looks like, by the way. So for example, it has the title of the PR, the body, the size label, the author, the interactions on the PR, and so on and so forth. So basically a bunch of raw data that's been collected from your PR. Yeah, so once you have this raw data, you can basically just package it into a JSON as a list of lists, essentially. And then send this JSON as a payload in a post request to the endpoint URL that we deployed. So this is the endpoint URL for our model. And here I'm basically just sending this JSON as a post request, as a payload for the post request. And bam, I get a response, 200, which means that it was a successful request. And yeah, it worked. So the output of this request is basically the two things. One is the classes that it's predicting for. So for example, class 0 represents merge within 0 to 3 hours. And then class 9 represents it's going to take more than like 3 weeks to merge this PR. So that's what the classes represent. And the other output you get is obviously the predicted probabilities for each of the PRs. So here you can see the highest probability is, for the first PR, the highest probability is for class 6, which means that this PR is likely to be merged in like 3 to 5 days. So yeah, just to summarize, what we did was take the data from the MI tool or GitHub API, package it into a JSON, and then just send it as a post request to our endpoint URL. And then you'll get these output probabilities, which you can use to triage the PR or estimate effort for your sprint and so on. So yeah, that's how you use the service. And I encourage you to check it out and use it in your project if you'd like. Yeah. So that said, there are still some things that we need to address. For example, right now it's been trained on one specific repository. So it might not generalize that well across all the repositories. So the accuracy might not be on par. So that's one thing we're working on. The other thing we're working on is integrating it into a thought bot, a GitHub bot. So you don't even have to do the data fetching and post request sending part. So what this means is you can simply create a new PR, and then a bot will swing by the PR and put a comment like this on it, that the estimated time to merge is more than 19 days. So this is something that's still a work in progress. It's on a test cluster, but that's in our to-do for next steps. And then finally, we want to set up model monitoring to monitor the model and reiterate on the model architecture itself to continuously make it more accurate. And I guess that's all from this sub-project. And then for the next section of the talk, I'll hand it over to Hema to talk about the optimal stopping point prediction.
Awesome. Thank you so much, Karan. I will take over the screen share from here. Just give me 1 second. Okay. All right. So I hope everybody can see my screen here. And just like Karan walked through one of the problems that we were trying to address, where we were looking at GitHub data to predict the time to merge for a given PR, another problem that we tried to look into is how do we predict optimal stopping point for running CI tests. And before we understand this, let's look at what exactly is the problem that we have here at hand. So oftentimes as developers and data scientists, we usually interact with a repository whenever we would like to make any changes to the code base. And this is usually done via a pull request. And every pull request is subjected to a set of automated builds and tests before it could actually be merged. And sometimes we see that tests may take longer running times as we expect them to. And this can lead to a certain bottleneck in our CI/CD process. And oftentimes we're just waiting for the tests to complete, and it can sort of block us from any progress that we would like to make for these application changes that we're looking into. So how do we optimize this running time of our tests and prevent these certain bottlenecks? And the solution that we thought of with the help of machine learning is, can we predict an optimal stopping point for a given test so that we can better allocate all of the resources in our CI/CD pipelines and prevent this bottleneck from happening in the future as well? So now that we know the problem and the approach that we would like to take for this, firstly, we need to think about what kind of data can we look into for this purpose. And Karan mentioned that he was looking at the GitHub data, but in this case, we look at something called as the test grid data. And the test grid data has a bunch of CI/CD jobs and tests that are running for different clusters related to Red Hat, like OpenShift clusters. And you can actually look at different tests that took place, as well as the timestamps of when a certain test was executed. And each of these tests also come with certain status codes. So for example, if it would be passing or if it would be failing, if it's a flaky test, and so on. So with the help of these test status, as well as the timestamps that we have allocated for each of these tests, we can start looking into this data and see if we can understand some of these metrics a little better, so that we can start thinking about the model that we would like to build out. So once we explored this test grid data set, we needed to start looking into what kind of features do we have from this data. So performing all of the feature engineering using the help of Python libraries and tools and Jupyter Notebooks, we started exploring these data sets. And we saw that test grid allowed us to extract this metric called test duration metric. And this metric is nothing but tracking the time that it took for a given test to complete its execution. So what we decided was, since we have this test duration metric, we can actually try to find out the distribution type of this metric for all the different tests. And based on the different distribution types that we identify, we try to compare the distribution types for the passing as well as the failing test. And we try to plot the probability density plots, which are used to understand the data distribution, and also the likelihood or the probability of obtaining a range of values that this variable can accommodate. And these plots actually give you the area under the curve, which actually would contain these probabilities for this test duration metric that we are interested in. And once we sort of understood what this probabilities and density plots looked like, now we had to think about training our machine learning model. So how do we actually predict that optimal stopping point? So since we had those durations for a given test, what we decided, and since we also had the probabilities, we decided that the optimal stopping point would be the point where the probability of failure for a given test was much higher than the probability of passing for that same test. And with the help of these graphs, you can actually find this point of intersection in those passing and failing distributions that I mentioned. And that intersection point along the x-axis would actually give you the timestamp or the corresponding test duration runtime at which this optimal stopping point can be determined. And once we sort of were happy with this model and how it was performing and giving us these predictions, we decided to package this, as Karan mentioned, so that it's available at an interactive endpoint. So we used the help of a Selden service for this. And similarly, we also created an inference notebook to check whether the predictions are being passed to that endpoint, and more specifically to make sure that the model is expecting to behave as it was supposed to. And we tried this out with a bunch of different test grid tests, and we started looking at the optimal stopping point that it was predicting, and just making sure that the endpoint is also giving us the output of this model. So once we sort of had all of this packaged and ready and accessible via an endpoint, we similarly, we also had an inference notebook that Karan showed as well. So let me quickly go over that over here. So this is actually our project repository. So we have a bunch of different models and notebooks associated for each of these different types of models. So as I was explaining the optimal stopping point, we have all of the overview, the data set, and also the different notebooks that we use to perform each of the feature engineering as well as the model training. So if you're interested, you can also go take a look at these notebooks, which are available on our project repository. And this is the model inference notebook that we have over here. So again, here is the endpoint of our Selden service that we would be interacting with. And again, as Karan said, we're basically sending to the payload the JSON of in this case, it would be the test that we are interested in to figure out what would be the optimal stopping point for it. So as you can see here, we have a given test name and then the timestamp also associated with it. So here we were just testing it out for a certain timestamp for that particular test. So we pass this as a payload for the endpoint of our Selden service, and then we send it as a post request. And once you can see that the endpoint is active and up and running, you should get a 200 successful status code. And once you have interacted with that, you can do a quick response.json to actually see what that endpoint predicted for this particular test that we were interested in. And this is giving us the stopping point in terms of seconds and telling us that this is where for that particular test, after this point, you should basically not continue your testing, because longer than this may result in your test to run into a failure state. So that's essentially what this particular model was trying to solve. And of course, there are definitely more areas that we can improve on, is basically how do we compare two different tests and thinking about if the relation between one test is affecting maybe the status of another test, and trying to find out if we can have this incorporated into our model as a future next step as well. And with that, I will end the stopping point model over here, but feel free to reach out if you're interested to learn more, and we can share the notebooks and the endpoint as well for you to try out. And I will hand it over to Shrey to talk about the next model.
Thanks, Hema. I'm just going to share my screen. All right, so another aspect of the CI data that we get from OpenShift is build logs. So Hema just showed the test script data, and so the jobs that are available on OpenShift contain a lot of tests, and each of those tests have a build log associated with it. So as a developer, if you have a test that is failing, you can go over to the build log associated with that test and try to find out what's going on and how can you fix it. So now when you have a lot of jobs, and for those jobs, when you have a lot of tests, you get the problem of having to inspect a lot of build logs. So we thought it make sense to have some analysis in place and some ML models that can help us reduce that space when we are trying to debug a problem. So in this next section, I'm going to walk you guys through a project where we took one of the OpenShift jobs, and for all the tests that executed for that job, we took the cluster build logs and did clustering for them. So the experiments where we do analysis and try out different clustering algorithm is available here in a video by Pep. And if you're interested, you can look at the whole data science workflow. Today, I'm going to focus on the endpoint, or the final place where you can access the clustering models and then basically plug into your own system of log files. So let's go ahead to a Smog Jupyter Hub instance and look at the demo notebook. So the build log EDA that I talked about has a notebook here as well. And this is a glimpse of how some of these log files look like. So we have the timestamp, and then we have a message that was generated when this test was running. So once we have that, we can do a lot of analysis with it, which is detailed in this notebook. Once we have that, we take the analysis from that and put it into a deployment endpoint. And this notebook goes over that. So first, we are going to load the data set. We define a job that we are experimenting with, and then for that, we load the data set of log files. Once we have that, we train a simple sklearn pipeline. So this pipeline is basically taking your log files, converting them into vectors, which can be then used by the k-means algorithm that would basically group these log files into buckets. So here we are using k equals 3, which was found in the analysis. So that means that we are taking all the log files and then putting them in 3 separate buckets. And at the end, whenever we have a new test run and we have a new build log, we know which group it falls into. And hopefully that saves developers some time into assessing why it's failing or why it's passing. So once we have that model in place, we save that on S3, and we create a Selden deployment out of it. So this is the base URL for the Selden service. And it's very simple to create it. It's just one manifest file, something like this, that says that this is going to be an sklearn server, and then it'll take a model that we just trained from this location on S3, and it's going to just spin up the deployment. When we have the route for the deployment, we can use that here to send payloads. So in the next step, we just take some of the test data set that we have, package it in a format that we can send over to the model endpoint, and then get a response. So response 200 means that we are able to ping it, and then it's replying. And if we just look at the JSON of that response, we would see the labels for the log files. So that's about it. So we saw how we can take these log files and cluster them and take this unsupervised learning model and put it on Selden deployment. So the next steps here would be to create a model for build logs from another job and experiment how this clustering algorithm works with another environment, and then also ask developers to validate some of the results that it generates. So with that, I'm going to hand it over to Oindrilla to conclude and share resources for you guys. Thank you.
Great. Awesome. Thanks, Shrey. Thanks for introducing the final service. Are you going to continue sharing? Okay, great. So if you want to engage with this project, there are various ways in which you can get started. And we have compiled a list of ways in which you can engage with this project on this URL that you see on the screen. So basically, you can interact with and leverage the various open source CI data sources that we talked about. and that we work on this project along with the data collection scripts and the exploratory analysis. So all of this data, we are also storing them on a public S3 bucket, so you can access them for your own analysis. We also have various interactive and reproducible notebooks for this entire project that are available for anybody to start using on the public Jupyter Hub instance on the Operate First cloud. We also have some interactive dashboards available which analyze the test grid data as well as the GitHub PRs. So you can check those out as well. And we also have the model endpoints that we discussed earlier available for you to try out. We also run these automated AI ML workflows using Elira and Kubeflow pipelines. So if you wish to run ML workflows or automate your Jupyter notebooks, you can also follow some of the guides that we have compiled. And finally, to learn more about the different analysis and notebooks within this project, you can also check out our YouTube video playlist where we often upload a lot of descriptions or lots of tutorials on various scripts and various aspects of this project. And finally, if you want to contribute to this project, this is a fairly new open source project which we started a year ago within our team at Red Hat. So if this project is useful to you, or if you're working on similar efforts, we strongly encourage contributions to this. There are various ways in which you can contribute to these existing notebooks or contribute additional KPI metrics analysis to this project. If you want to contribute to the work of developing additional KPIs and metrics, we also have a video tutorial and a helper notebook which outlines the templates for that. And if you would like to contribute to an existing ML analysis or model, let's say one of the ones that we discussed today, we highly encourage that as well. And if you would like to add your ML analysis and model, we also have some issue templates for you to contribute to those. And thank you. Thanks for tuning in today. Here we have some of the links to the repo and the website where you can find us. So yeah, thanks for joining. Please let us know if you have any questions.
Cool. Thank you all so much for doing that presentation. I really appreciate it. That was a lot of cool, interesting stuff. Cool. So does anybody have any questions? Thanks, Surya. Great. Well, so I guess if there's no questions, I added some links to the chat so everyone can check out this project in greater detail. As we said, the video will be uploaded to YouTube so people can watch it in the future. Yeah, I hope this was interesting to everyone. If you have feedback or ideas around how to extend some of these AI services or make new ones, I think that would be something we'd be all very interested in hearing. So cool. Well, thank you all, and I will see you at the next Operate First Data Science Community Meetup.